Okay, so next up we have Jinyi Yang from UMich telling us about early supermassive black holes.
Okay, thank you for this opportunity. I'm Jinyi Yang from University of Michigan, and I'm working on high-redshift supermassive black hole, particularly high-redshift quasars. So today I will talk about what my group will do in the next few years using Roman and LSST to work on high-redshift supermassive black holes. Okay, so a few information about why we will care about high-redshift early supermassive black hole or high-redshift quasars. So they actually can provide us with unique, valuable information for the early universe from different scales, different aspects. So from the left side, oh sorry, doesn't work. Yeah, the left side, so small scale, talk about the seed black hole model, black hole growth, early growth models. And if you do bigger scale, we'll see, okay, that's the black hole, sorry, you just,
you have to press and hold.
No. But it's okay, yeah. So we can see in the middle. Okay, yeah, thank you. In the middle, so that is the black hole feedback and the black hole host co-evolution from very early stage. To even bigger scale, we will talk about using this luminous quasar early supermassive black hole. We can trace overdense environment in very early universe. That's the formation of early large-scale structure. At the same time, we can also use this bright object to study, to investigate cosmic realization history. So that is why we care about this object. Yeah, I can use that one. Thank you. Okay, so today in this talk, I mean, you will hear about large-scale structure in next talk, but for my talk, you'll hear more about early black hole growth and black hole host co-evolution can be mainly described by this figure, that is how the black hole and host galaxy grow together, or any one can grow first and with another one catching up later, and then to form the relation we can observe today. However, actually, we don't know about high redshift. What we know, we observed the local nearby universe, the famous M-sigma relation from galaxies, agents, and local nearby universe. However, we have only limited knowledge about high redshift objects as limited by observations. But now, it's actually a few more background information about what we have learned in the past 3 and 4 years from JWST. So for this high redshift quasars, JWST helped us confirm the existence of billion solar masses black hole at redshift 6.5 up to 7.6, so which means 1 year or just 700 million years after the Big Bang. And then significantly challenging the seed black hole model or black hole growth, we need 1,000 or a few 100,000 solar masses seed black hole at redshift 20 or 30, or we need ideal accretion, super hyper ideal accretion, all the way started from very early stage. At the same time, for the first time with JWST, we can direct image, stellar emission from their host galaxies, and then we found, oh yeah, there's something keyword, but diverse host galaxies, we see and complicated small-scale environments, we can see multiple close companions, extremely extended structures around these high-redshift luminous quasars. And with this information, we can now look at the black hole host relation in these high redshift quasars. So this is a new result from our high redshift luminous quasar sample. So now we can see that there's a correlation between this high redshift black hole mass, high redshift quasar black hole mass, and stellar masses. So we see this relation in this high redshift quasars. However, something interesting from UV luminous quasars, we see that after counting for selection effect, and uncertainties of measurement, we see this luminous quasar still sit above this local relation. However, UV faint quasars, this open orange squares, they tend to follow this local relation. However, with larger scatters. So we see some difference from UV luminous or UV faint quasars. It's still something we haven't really understand that. In addition, we see strong black hole feedback in these luminous quizzes. For example, let's try again. Yeah, that one. Okay, so we see the near-spec FU result directly captured of this kind of strong oxygen-free outflow from near-spec FU data. At the same time, 1D spectral from JBST show significantly blue-shifted and broadened oxygen-free doublet tracing galactic skew outflow. For this one, this is the most extreme case with about kinetic power about 10% of the quasar bolometric luminosity. So based on simulation, this kind of strong galactic outflow can significantly affect the star formation activity in the host galaxy. So this one, focusing on this system, we have ongoing detailed analysis for that one. Okay, so this is what we have learned from JBST. And back to black hole host, the first question now we can answer that yes, in this high redshift luminous quizzes, we see a relation between black hole mass host galaxy. However, there are a few questions left, or just arised by the recent JBST observations. So now we want to answer is when and how this kind of black hole host relation form, and whether and how this kind of relation involve over cosmic time. So this is what we can answer with Roman, Rubin, and Euclid. It's a new era for this kind of study. Okay, as the next step, just in the next few years, what we want to target, so two categories. The first one, we want to directly observe high redshift quasars, high redshift supermassive black holes, so that is redshift about 7 quasars. At the same time, we also want to target little red dots at redshift 1 to 2. We have heard many great talks about little red dots these 2 days. So my talk will focus on redshift 7 quasars more, but we will also mention a little bit. So why we at the same time care about redshift, lower redshift, little red dot, broad aging, because we want to test whether they represent a special rapid early black hole growth phase existing only at high redshift. So the third one is just from the selection of these two categories, we always get the third one, radon and obscure agents. So I will not talk about details today, but if anyone who is interested in that, I'm happy to discuss more details. Okay, the first one, redshift 7 quasars. This slide just show that is how we can have a large sample with JBST today. It's just in the past 20 years, over this effort, our survey started 10 years ago, so it's actually challenging to find this high redshift quasars. 2 reasons. Left one, the rapid number density decline as a function of redshift, particularly a redshift about 5. At the same time, we get high contamination rate. The main contaminant of high redshift quasar survey and multi-dwarfs and red galaxies, they can have 1,000 to 100,000 higher number density than quasars. As a result, it's very challenging to detect high redshift quasars. And the right one, that figure shows what we got in our 10 years high redshift quasar survey. We actually constructed this largest high redshift luminous quasars up to 7.6, and this is what we are observing today with JBST. And we are entering a new era with Roman, Rubin, Euclid. So things will be changed. Over these 3 missions, or 3 telescopes, we have different survey field, different depths, different spatial resolution. And we see the depths, particularly when we have Roman plus LSST, we will have the wide field image from optical to the near infrared. As a result, we can predict how many quasars we can cover in this new era. It's just that we have LSST, Roman, Euclid to cover quasars. Again, this dashed line is the depths we have today. It's our today's survey, 21.5 J-band. And we can see with Roman, Rubin, and Euclid, we actually can improve that. We can push to down to 3 or 4 magnitude deeper. We can improve the data set, the sample of high redshift quasars by more than 1 order of magnitude. A few early results from the first year, our Euclid high-Z quasar team just published the paper last week. We got it's actually just from our first observation, we got 30 quasars with 12 above redshift 7. And we have the new redshift record breaking quasar at redshift 7.77. So this is just from Euclid first year observation. And you may see a paper about Euclid redshift 8 quasar very soon. So this is from the Euclid Earth sample. And what we can do with Roman is the next 2 years. First, Roman's grism data will provide us directly with spectroscopic data. As a result, we can predict this kind of spectral data will cover a few to 12, more than 10 objects, quasars are redshift about 7.2, or in the deep tier, we can maybe one or several. It's actually this kind of large uncertainty caused by different quasar lambda function. Here's one simulation. If there's one redshift 8 quasars brightest one, we can cover that directly with quasar spectrum. In addition, we also have deep imaging data. We can have imaging selection plus spectroscopic follow-up probably from JVST. Then we can cover more quasar candidates, cover more quasars redshift above 7. For example, the Roman and LSST selection, we can up to like few tens. If we go deep tier, it's actually we have deep optical, deep Z-band by Roman itself, then we can cover like redshift above 7 quasars, about 100. So this kind of large uncertainty from quasar lambda functions. So which means the Roman sample will directly help us to distinguish between different quasar lambda function at the front end and help us to constrain quasar contribution to the ionizing photons. Okay, that's the high Z quasar part. The last 2 minutes, I want to talk a little bit about laterite dot. I think I can skip this slide because we have heard many things, many unique properties about laterite dot, why laterite dot interesting. And what I want to do is actually we want to have a large uniformly selected sample from Roman and LSST. So to answer the questions why there is a supermassive black hole existing in the center and whether laterite dot can really represent the special fast growth phase of the supermassive black hole existing only at high redshift. And the last one, whether they have the same structure as AGNs, we know. Okay, to answer these questions, what we can do the next 2 years, we can have Roman plus Rubin plus LSST selection for the laterite dots or broad AGNs at redshift 0.5 to 2.5. So imaging selection or SCD selection from Roman and Rubin is kind of photometric data set. At the same time, we have broad emission line selection from Roman directly to cover H beta HR lines. And the next step will be variability studies from Rubin. So it's kind of systematic large sample variability study from LSST so we can better understand structure of this kind of object. And, okay. And the next one is just a summary. So we see the number density figure again. So what we want to do here, 0.5 to 2.5, filling the gap between local laterite dot and JVST laterite dot. So we want to answer. So we can also predict in the next 2 years, there can be a few hundred to a few thousand. Again, it's kind of uncertainty because we don't know the exact number density redshift evolution. Then we will know that from the Roman LSST selection, and we will also know the structure, constrain the structure from LSST variability analysis. Okay, I think that's my last slide summary. I will leave it here. Thank you.
Time again. Questions for Jinyi?
So just a very maybe a general question. My understanding is that right now reionization is really driven by galaxies. The reionization is driven mostly by photons from galaxies. Do you think at some point AGN at higher redshift can contribute a meaningful amount to the photons needed to reionize the universe?
I think your question is about ionizing photons. Yes. I think from most recent observations, you should say galaxies play the dominant sources to the ionizing photons, but AGN and quasars, they also play an important role. At the same time, it's actually there should be a large uncertainties depending on, as I mentioned, the quasar lambda function or AGN lambda function, particularly at the fin end. And this is something we haven't really constrained that. We need this kind of deep survey to really constrain the AGN fin end luminosity function, and then we can answer the question, what is the exact fraction that AGN contribute to the realization, I think.
Other questions for Jinyi? I actually had a bunch, but I'll limit myself to one. You mentioned that it will be interesting to figure out how and when, the the black hole galaxy coevolution started. How would you go about doing that? Because a lot of times when we're looking at these early objects, we're relying on local relations. So, how do we know actually when that relation was started? Or what kind of scatter requirements are we looking at?
Yes. I think we need to constrain this kind of black hole growth history and the galaxy assembling to higher redshift For example, recently there are 2 UV fan quasars get already observed stellar absorption features and show post-starburst signature in the spectral, and then we know there should be a starburst like a redshift about 7 or 7 to 8, something like that. So this can tell us that's the fast assembling epoch of this host galaxy. So we need a larger sample with this kind of constraint, then we will be able to know the growth history of both black hole and galaxy for this, high redshift quasars. Okay.
Thank you. Other questions for Jinyi? If not, then let's thank Jinyi again.